A DLList, or doubly-linked list, implements the full list interface and also provides an efficient implementation of the deck interface. The basic building block of a DLList is a node. A node has three parts: a piece of data that we call X, a pointer to the next list node that we call next, and a pointer to the previous list node that we call prev. The nodes of a DLList are linked together, one after another, through their next and prev pointers. To make things simpler and avoid special cases, it helps to introduce a special empty node that we call the dummy. The dummy's next pointer points to the first node in the list, and the dummy's last pointer points to the last node in the list. We can think of the dummy as a node that appears both before the first node and after the last node. The DLList itself consists of the dummy node and an integer n that keeps track of the number of items in the list. Most of the work required in implementing the list operations comes from finding the node in a DLList that has a specific index I. This is done by a helper function called getNodeI. To get the ith node in a DLList, we first check if the ith node is in the first or second half of the list by comparing I to n over 2. If I is less than n over 2, then the ith node is in the first half of the list, and we can get to it by starting at the dummy and following I plus 1 next pointers. If I is bigger than or equal to n over 2, then the ith node is in the second half of the list, and we can get to it by starting at the dummy and following n minus I prev pointers. Putting all this together, this means that we can get to the ith node in a DLList by following the minimum of I plus 1 or n minus I pointers. This means that the getNodeI function runs in O of 1 plus the minimum of I, n minus I time. It takes at least constant time plus time proportional to the minimum of I and n minus I. With the getNodeI function, getting and setting values in a DLList becomes easy. To get the ith value in a DLList, we just get the ith node and return its value. This takes only constant time once we've found the ith list node. To set the ith value in a DLList, we just get the ith node and set its value. Again, this takes only constant time once we've found the ith list node. Adding and removing from a DLList is also fairly easy, but requires some careful pointer manipulations to get everything working just right. To add a new value to a DLList at position I, we first create a new node U that contains the value we want to add. Next, we use the getNode function to find the node W currently at position I. Now we have to set 4 pointers to splice the new node into the list. 2 of these pointers are in the new node U. One pointer is W's prev pointer, and the last pointer is in the node that appears before W. These pointer changes only require 4 lines of code, but it's easy to get them wrong. Finally, we increment the value n, since the list now contains one more value than it did before. Note that adding the new node U to the list implicitly changes the indices of all the nodes that come after U. As with the other DLList operations, add IX only takes constant time once we've used getNodeI to find the ith node in the list. Removing the ith value from a DLList is a bit easier. We first use the getNodeI function to find the ith list node U. Next, we update 2 pointers to splice U out of the list. One pointer is in the node preceding U, and the other is in the node that comes after U. If we're working in a programming language that requires explicitly freeing memory, then we should now free the space allocated to node U. Finally, we decrement the value of n since the list now contains one less value. Note that removing the node U has the side effect of implicitly changing the indices of all the nodes that come after U. Again, the remove I operation only takes constant time once we've used getNodeI to find the ith node in the list. To summarize, a DLList implements the list interface so that each of the operations getI, setIx, addIx, and removeI runs in time O of 1 plus the min of I and n minus I. When we specialize this to the DEC interface, each of the operations add front, add back, remove front, and remove back runs in constant time.